Good evening to everyone. In continuity of the previous class, we were discussing about degree of reaction for a particular reaction turbine, where we mean that the 50% of expansion, that means the expansion is being carried forward equally on the fixed blade as well as the moving blade. Then we can even say that in other terms, like 50% of expansion is over the moving blade and another 50% is over the fixed blade, right? In that condition, what would be the pressure line and what are the points that you are trying to represent it in form of an enthalpy drop in with respect to the pressure line that are available for us, right? And now why we are trying to express this in terms of enthalpy means that the degree of reaction for any of a reaction turbine is mentioned in terms of enthalpy drop. And how it is being defined? And it is given in terms of enthalpy drop over a moving blade to that of a total enthalpy drop over entire stage, that is from starting to the ending. Now we will have drawn the picture and we will see what would be the degree of reaction expression for this Parsons reaction turbine, right? From the definition, I can write degree of reaction equals to H2 minus H3 divided by H1 minus H3. Right? Is this the expression that we have discussed in the previous class? Now we will try to write the expression for the fixed blade and the moving blade and for the total enthalpy line. Right? For fixed blade, what would be the expression? Fixed blade, it is nothing but delta H is H1 minus H2. Why I have given for H1 minus H2? Why can't I go for H2 minus H3? In the previous class we discussed and we have drawn the pressure lines having the first fixed blade and then the moving blade, right? Fixed blade inlet is represented as 1 and the outlet is 2. And the inlet of a moving blade will be 2 and the outlet of a moving blade will be the 3, right? For a fixed blade of having delta H equals to H1 minus H2, it is represented in terms of VR. 1 minute. H1 minus H2, fixed blade, it is not moving, right? Then I have to consider the absolute velocities, not the relative velocity. If I represent or if I talk about a moving blade, then I can say that it is a relative velocity. Why? Because here the blade is also moving with respect to the jet, right? Here we are discussing about a fixed blade. It doesn't have any relative velocities. It has only the absolute velocity of the steam at the inlet as well as the outlet, right? It is V1 square minus V2 square divided by 2000 kilojoule per kg. Similarly, for moving blade. Now if I consider moving blade, it is the V1, V2 or VR1, VR2. It is moving blade, right? Therefore, delta H will be from H2 minus H3. Since it is a moving blade, here I am going to consider the difference of relative velocities, right? H2 minus H3. Now it would be relation VR2 square minus VR1 square divided by 2000 kilojoule per kg. If I want to find out the total enthalpy drop over a stage, then what can I do here? This is the enthalpy drop over fixed blade plus moving blade. Can I say this? Yes. Now we will write why, because we have the relations for the fixed blade as well as the moving blade. If I add that, I can get the value of total enthalpy drop over a stage. Right? Now total enthalpy drop, that is H1 minus H2 plus H2 minus H3. It is nothing but H1 minus H2 plus H2 minus H3. If I cancel out H2 plus and minus, I'll be ending up with H1 minus H3. Right? It is nothing but, since H1 minus H3 is the delta H for entire stage. With the entire stage, right? Now I can add these two. Then finally I can get the relation for the enthalpy drop for the entire stage, right? Now H1 minus H3 equals to V1 square minus V2 square divided by 2000 plus VR2 square minus VR1 square divided by 2000. Right? And since the blades are symmetrical, we have a relation VR2 will be always greater than VR1. And still we have a relation for the Parsons turbine, reaction turbine. V1 equals to VR2 and V2 equals to VR1. Right? This is the condition. If you want, you can remember this, and you can even place it in the box. Now, from this, you can write the relation H1 minus H3 equals to 2 times of VR2 square minus VR1 square divided by 2000. Yes, or simply I can write the relation 2 times of H2 minus H3 kilojoule per kg. Right? And now can write the relation here. Degree of reaction for Parsons reaction turbine is H2 minus H3 divided by, you can put this H2 minus H2 in the bracket, 2 times of H2 minus H3. H2 minus H3 divided by 2 times of H2 minus H3. Can I cancel out these terms? Now what I am left out with? 1 by 2. It is nothing but 0.5. If I want to represent in terms of percentage, it will be 50. Therefore, degree of reaction for a Parsons turbine is equal to that of 50%. Right? Now can I say that in a turbine, a degree of reaction of 0.5 can be the general value. If the degree of reaction is 0.5 or the 50%, I've derived the relation for this only for the Parsons reaction turbine. On this basis, Now we fixed a degree of reaction value to be of around 0.5 to 0.6 for any of the turbines, right? When that range is about 0.5 to 0.6, we call such turbines as the impulse reaction turbine. What is the condition here now? You can write it as a note. If the degree of reaction ranges from 0.5 to 0.6, we call the turbine as impulse reaction turbine. Right? Am I clear now? Am I clear? Now we will look at the next relation. First relation, what we have derived? We have written the expression for work done, and then we have written the relation for power developed, and the third thing we have discussed about the degree of reaction. And what is the relation we have? For any of the degree of a reaction having the value of 0.5 to 0.6, we call that turbine as impulse reaction turbine. Now we will look at the next topic under reaction turbine, how to find blade height. How to find the blade height, right? And what are the parameters that I have to consider in order to find out the blade height? If I know the relation for the blade height, then I'll think of like what are the terms I have to consider and how it will be, and is there any relation I have for this blade height. I don't know where we have. If you remember area relation, how the pipe is, generally we take it as like a circular, and now one part, if you look at one part, it will be a circle and other tip as a point, right? And now whenever we see that there is a volume of a flow over certain area, volume means area multiplied by the height, right? Here if I see the volume for a flow, I can relate it to the flow area to that of velocity of flow. Flow area means around the diameter to certain height. There I can come across the height. There the height is represented as the blade height. Okay. In that way I can, if I am able to derive a relation for the volume of a flow, I can get the relation for the height of a blade. Right? Yes or no? Yeah. Now the flow area is the annual area that we are going to consider to derive the relation for this blade height. Now with this, what is the flow area, how to get it? Is there any relation with the flow area? Yes, we have one relation. Volume of flow, how much of the flow is entering into the blade, how much of a steam is being flown into the blade to a certain height, through a certain cross section area, and with some velocity, right? Now if I consider all these three, is there any relation? Yes. Flow area multiplied by velocity of flow, right? And now I'll write the relation what I know for the flow area. Since it is circular, pi d suffix m. What is this d suffix m? Mean blade diameter. I'll write it separately here, right? And through this area to certain height, having a certain height, the velocity of flow is flowing, right? The velocity of the steam is flowing with a velocity of v suffix f. V suffix f represents the velocity of a flow. This steam is flowing through this flow area, and this is represented as pi multiplied by d suffix m into h, right? Again still we can represent it as volume of flow equals to pi dm into h into Vf. Now you have to remember this relation. Yes. Now we'll go for the another one.